The purpose of this video is to show you how to reduce the results of your consolidation tests. And I'm going to do it by showing some example results to begin with. Now, the measurements that you make in a consolidation test are basically simply time and a dial reading which measures the change in height of your sample. So basically time and change of height. So we have time, in this case we're going to use seconds, and delta H in feet. And so in that sense, the data that you're recording is extremely basic. But to reduce the data and get the soil properties that we want is a little bit complicated, and that's why I'm making this video so that it makes some sense to you. Now, in this particular example, we have the time listed here and the delta H for all of the different days here. So we have day 1 delta H's, day 2 delta H's, day 3, day 4, day 5, day 6, day delta H's, all those in these columns here, and we go up to day 12. Now, what changes each day is the load that is put onto the sample. So this load in pounds, so in day 1 we put 3.5 pounds on the sample, and we measure the delta H with time. On day 2, we have 5.25 pounds on the sample, and again we measure delta H with time. So each day the load changes, so we have the different loads, and we get different delta H's for each load. And most of the time, we are increasing the load. So 3.5, 5.25, 7, 9.45, 12.25, 17.15. But then, in this case, in day 7, we go from 17.15 down to 8.05. And then it drops again to 3.5. Then it goes up again to 8.05, then 17.15, then 28.59.5. So we increase the load during the first 6 days, then we drop the load for a couple days, and then we increase it again for the last day. So we have to remember that we have a different load for each day. And of course, we have different delta H's for each day. But in this case, we're taking the readings at the same time. So in other words, at 2 seconds on day 1, at 20 seconds on day 1, at 100 seconds on day 1, and we do the same times for all the different days. So what we want to do then is we are going to plot all this data. We have to plot all this data, and I'm going to show you the way that the plots are made, and then what we are going to calculate from those plots. Now, the way that it's going to be is we're going to have a different plot for each day. So this works out pretty straightforward. So if we're going to take this data right here, and we're going to plot it with time in seconds on the x-axis and delta H on the y-axis. Now, just a couple things about this. First of all, it's a log scale for time. And so remember how we have a log scale. At these equal sections, we go up by a factor of 10. So this is 1, 10, 100, 1,000, 10,000. And there's no zero on this plot because it's a log plot, so that causes a little bit of an issue, but we're going to deal with it later. But now, the delta H, the way this is traditionally plotted is that we have small numbers at the top and we have big numbers at the bottom. So in this case, because it's day 1, we're going to have 0 at the top. And but we're not always going to have 0 at the top. Now this is an arithmetic scale here, so we do have a 0, or a 0 does exist on the plot. Now, so in this particular case, what we do is we look at the data here. We have to figure out what our y-axis is going to look like. I have to choose the scale. I have to choose the scale. Now you can plot it automatically, or you can you can use Excel or something like that, but I'm going to show you how to do this by hand. It's pretty straightforward. Now, what we do is we look at this data here, and what we find is that the delta H, this is the raw data that you've made from the consolidation test. We have a delta H of 0.0188 feet at 5,000 seconds. So that means I've got to, I have a very tiny number here, so I start out at 0 at the top, and then I have to go to 0.0188. So, in this particular case, I go down to 0.02. So these points are plotted, I don't show the points, but this black line has these points. I'll show you the first one, 2.004. So at 2 seconds, remember this is a log plot, that's 1. This is 2. So at 2 seconds, well, basically we're right there. Okay. At if we pick another point here, say 100.01. So 100 is here, 100, and then this is 0.01. We're right there. So the black line on this plot represents the raw data. So this raw data is plotted, and it creates this black line. For day 2, it's similar. We do the same thing. I have this raw data, and it creates this black line. Now the only difference is that when I plot day 2, you're going to notice that I'm not going to start at 0. I don't have 0 at the top here. Well, what am I going to use? Because I need to see this line, and if it starts at 0, it gets messed up. So instead, I look here at what my bottom point is. So I'm looking at my bottom point, which is for my delta H is 0.0188, and so when I look at and when I make my plot, well, I'm going to start with my plot pretty close to that. I need to show the 0.0188 because that's my first data point here. The way that it works is that the last point on day 1 becomes the first point on day 2. So I'm going to start up. When I create this scale, I'm going to have to put on my 0.0188 up at the top here. And then my bottom point, in this particular case, we stopped at 2,000 seconds, is 0.024. So I need to be, I start at 0.018 here, and then I need to go to 0.024. So I have 0.024, and if I space it out at 1, so this is 0.018, 0.019, 0.02, 0.021, 0.022, 0.023, then this becomes 0.024. So that way I don't necessarily have to go all the way to the bottom of this plot, but I use a little bit more than half so that I can see this line. In other words, I don't want to create 0.018 here and then have 0.024 here. If I did, then what would happen? Then my line would look something like this, or something like that, and I wouldn't see anything. I've got to have this spread out a little bit. So again, this data here is this line, and by choosing the right y-axis, I'm able to get that line, cover half of my or more of my graph so that I can see it. So that's how I choose my y-axis. Okay, so once we've done that, then the point that we're going to be most interested in for the first part of this, of developing this data, is the last point. So we're going to be interested in the 0.0188. We're going to be interested in the 0.024, and of course we're going to be interested in the load. So I have the load here is 3.5 pounds. That's for day 1, and the load on day 2 is 5.25 pounds. That's for day 2. So we're interested in really the load and the last point for the first data that we want to reduce. So there's the load, there's the last point. So you can get that from here are the loads here, and here are the loads here, and then you get the last points. It varies whether we went to 5,000 seconds or not, but we get the last points there. So we have the data that we're interested in to begin with. Then what we're going to do is okay, well, first of all, you have to plot the data. So let's go back a little bit. Now, so in other words, here's the data. I've only plotted for you day 1 and day 2. You have to plot these data, and so you got to plot that. Okay, so what's it going to look like? They're going to look like these plots here, and you're going to put it on this. So you can reproduce this particular page. I've plotted the time here, so we go up to 10,000 seconds, 1 second. But again, you need to select the correct Y scale. You can also do this on Excel or something, but it's a little bit tricky on Excel because but just let you know, it's okay to do it that way, but you're going to have to draw the line connecting the points. It's not a straight line. Okay, so, okay. So, the, well, okay. Like I say, there's different things that we need to calculate, and what we're going to do after you plot it is we're going to look at, actually we'll look at the whole plot and then we'll get down to those last points that I was talking about. But what we're going to do is calculate the value of the coefficient of consolidation, value of C sub v, for days 3 to 6 and 9 to 12. We're not going to do it for days 7 and 8 because those are the unloading days. So I'm going to go through the examples of how to do this for day 1 and day 2. You need to do it for the other days. And this is a little bit of a cookbook, so I'll apologize for that, but people who have studied this problem came up with this method to get this property. And I don't want to go through the theory of it, but right now I just want you to do the cookbook and get the values. And the cookbook consists of these 8 steps. They are to draw a tangent line in the middle of the Z. What do I mean by the middle of the Z? Well, this is sort of the Z. You can see sort of a soft Z. And, this is a Z. That black line is a Z. So we have the middle of the Z. And, the middle of the Z, what do I mean? This is the middle of the Z in here, in this region. And this is the end of the Z in this region. So we're going to draw the first 2 steps are to draw tangent lines in the middle of the Z and the end of the Z. Well, so here's a tangent line in the middle of the Z, and there's a tangent line toward the end of the z, and we're going to get this intersection point is going to be important here. So let's look at these steps. So again, here's a tangent line approximately in the middle of the z. This is all approximate tangent line at the end of the z, and we get the intersection point. So the steps are draw tangent lines in the middle of the end of the z, get the intersection point, and get the delta h at that intersection point, and then get the delta h at 2 seconds. So how does that look on this? That means that I get the here's my intersection point, I get the delta h here, so I read off that value. I get the delta h at 2 seconds, I read off that value. Show it on the other one. So here's our intersection point. I get the delta h here, right there. Here's my 2 seconds. I get it here. I get that. So I have those two delta h's. And then, oops. And then what I'm going to do is I'm going to split the difference. So this is number 3 is the delta h at the intersection. Number 4 is the delta h at 2 seconds. And then I'm going to get the average of those two, which is 3 plus 4 over 2. And we're going to call that delta h 50. So that's a little calculation. I'm going to put these values on the table shown. And then I'm going to find T50 from the plot. Well, what does that mean? So at delta H50, I'm going to get my delta H50, so it looks like this. So when I do these steps, so I'll show them one at a time here. So step 1 so step 1 here is the tangent line in the middle of the z. Step 2 is the tangent line at the end of the z. I get the intersection point. I read off that. That's step 3. I get at 2 seconds. That's step 4. I calculate out step 5 is to get the delta H50, which is take the average of those two. And in this case, the average of those two comes out to be 0.0086. So I come over here at 0.0086, I go over, hit the curve, go down, and I read off this value of time, which is 80 seconds. So that gives me step 6. So that's my step 6, is to get the T50. And then I'm going to get what my HDR over 2, which you should know at this point what HDR is. That's the, in this case it's double drainage. The test itself is double drainage, so it's going to be my H over 2. Well, my H initially is 0.15, but now it's shrunk down by that amount, by the delta H50. So to get my HDR, I have to subtract that, because it's, that's the delta H that's taken place. So it's no longer, the thing is no longer 0.15 high. It's 0.15 minus 0.0086. I divide it by 2 to get my HDR, because it's double drainage. I get my HDR, and then that's step 7. Then step 8 is I'm going to use the consolidation equation, which is the definition of C sub v, the coefficient of consolidation, which is capital T times HDR squared over small t. And you can look at the lecture notes to see what capital T is, since we're doing everything at 50. This is my 50 times 50, so I have big T sub 50, HDR squared over T sub 50. So if we look at our consolidation curves, big T sub 50 is 0.197, and then I just got T50 here, which is 80 seconds, and I have my HDR here, so I have everything in this. So I have 0.197 times the HDR squared over T50 goes there, and I calculate out my C sub V, which is 1.23 times 10 to the negative fifth square feet per second. And then I'm just going to let you do that. Often this is in feet squared per year, so you have to convert that to square feet per year. I get 388 square feet per year just by converting seconds to years. And similarly, we can do the same thing for day 2. So it goes like this. Step 1, draw that tangent. Step 2, draw that tangent. Step 3, take the intersection point, go over here, get that value. Step 4, get the value up here. Step 5, take the average of those two. Take the average of this one, oops. Take the average of this one and this one. I get 0.0211. I then come at that average, I come over here, hit the curve, come down, I get my T50 is 50 seconds, that's step 6. Step 7, I subtract the 0.021 from the, remember that's my H naught, 0.15, that's the original height of the sample. I get my HDR by dividing that by 2 for double drainage. And then, so now I have my T50, I have my HDR, I plug those in, so that goes in there, that goes in there. My T50 is always 0.197, so you don't have to worry about that. And then I get my C sub V in square feet per second, and then convert it to square feet per year. So that is how you get the C sub V for each day. So you're going to get a different C sub V for each day. So this is the you need to fill out this table, and I've filled them out for the first 2 days for you, and we get our C sub V in square feet per year, but you can see delta H50, T50, HDR, C sub V, fill those all out. So you got to show all the values in this table. And then when you get all done, you're going to get a bunch of different values of C sub V. You don't have to do days 7 and 8 because those are the unloading days. But you then simply take an average. We're just going to take an average of those values of C sub V. Okay, so that's able to get the C sub V values. Now, how do we use the raw consolidation curves to get C-eps-r and C-eps-c? Okay, so now I had to create new fake data for you because to show you how to do this, I have to show a complete set of 12 days. So I created new data. So a completely different set of data. We're going to get completely different results, and I've simplified it. So now I put, here's my day 1, day 2, day 3, day 4, day 5, day 6. On the next page, day 7, day 8, day 9, day 10, day 11, day 12. So I just didn't do them all on different pages. I just, I'm trying to save space here. So in this particular case now, like I said, we're going to be interested in the last point. So, and we are going to be interested in our sigma here. How do I get my sigma? Well, I take the load. In this case, my day 1 load is 5 pounds, and my cross-sectional area of my sample is 5 square inches, which is 0.034 square feet. And so P over A gives me my sigma. And since at time infinity, or at 24 hours, there's no excess pore pressure, so sigma is equal to sigma prime. And so I get 147 P over A is my sigma prime. And then I have there's my last delta H. My H naught is 1.5 inches. I've done this in inches in this case. And then I can get my epsilon V is simply the 0.011 divided by the 1.5. And we get the epsilon V at 0.0073. And we can do that for each one. So you have the 0.1735 over the 0.15 to get the epsilon V. And then the sigma here is the P over A. In this particular case, P is 10 pounds. So that gives me 294. Just randomly, P is 20 pounds, so my P over A gives me 588. And then we use this for our delta H, that for my H. So I can get for this, you can do it yourself, but we get all of these values, we just get those two values. That's all we want. We want the sigma, and we want the epsilon V. And you can do the calculations yourself, but what I did, I came up with all the sigmas. So here are my sigmas for the different days. And here are my epsilon V's for the different days. Those are days 1 through 6, 10 to 12. And just to let you know, we also have to put on 7 and 8 and 9, which are those. And they're given there. So what we do is we plot them on my epsilon V log sigma V prime. So again, I have to put this on a log scale here. So you got to put it on your log paper. And you put all these different points. And if it's a good test, you're going to have two slopes, a slope there and a slope there. And then you have to get the slopes of those lines. And the way to do that is, basically you've got a straight line here, you got a straight line there. The only trick is it's a log scale. But we know that slope is what? Delta y over delta x. And so my delta y is my delta epsilon v. And my delta x is delta log sigma v prime because it's a log scale. And so this is my slope for C-eps-c. This is my slope for C-eps-r. And so this is sort of fake data, so all the points look fantastic. They're all on the line. So, but if you have you draw the line there as a best fit, and you want to choose 2 points on the line. In this particular case, I chose 2 points. I chose 0.4 and 0.1. So I choose this point and this point for my C-eps-c. Why? Because they're on the C-eps-c line. So I can't choose 0.8 here because that's not on the C-eps-c line. So I choose those two. And so I take the 0.2875 goes here. I take the 0.073 goes here. I take the 882, it goes there. And I take the 147 and that goes here. And I get my C-eps-c of 0.36. So notice that it's a log, like I say, in the denominator. So the delta log, my delta log is what? The log of one minus the log of the other is the same as the log of one over the other. So we have, that's why we have the log of 882 over 147. And yeah, so that gives us our value there. Similarly, for C-epsilon-r, I've got to choose 2 points on the C-epsilon-r line, which is here. So I'm going to choose 8 and what was it? 3, or sorry, I chose 7 and 8. Yeah, so I did choose 8. Okay, 7 and 8, and similarly, I have what? I've got the for 0.7, I've got 3880. That goes here. The 3745 goes there, and then the 1176 goes here, and the 588 goes here. And I end up with 0.045 for the C-epsilon-r. That is how you do it. You need to do it for your data. Now, let me just note that, these are the points that are plotted here. And so we, this is the delta, this is the epsilon v that is plotted here, I should say. And, you can get the stresses from each day. So we have the different days, we have the epsilon v's. So this is how we, you gotta put these points on this plot. And what you need to do for your data is you need to fill out this table. So in this particular case, you got the different days, you've got the loads. You convert those to sigma v prime divided by the area. You have the delta H. It's from the last point on your graph. And then, the delta H over H gives us our epsilon v. So we get our epsilon v's. And so you're going to fill out for all the different days, so you got 3 through 12, and you are going to calculate out the sigma v primes and the epsilon v's, and then you are going to put them on this plot. I plot point 1 is here, point 2 is here, and you're going to plot your points the rest of the way, and you are going to get, you're going to get points. I don't know where they're going to say they're over here. You're going to draw a straight line through there, and maybe you'll have points there. It goes like that. So you're going to have two different lines, and you're going to calculate out your slopes here. You're going to put your answer. You're going to put out you're going to put your calculation there, show the calculation, and then you're going to put your answer right there. So what you need to do then, so that is, this is an extra sheet. You can use this, so if you mess up, you can use another sheet, or if you have other data. I've already put 2 points on this data. And so your end result is, you've got to fill this out. You got to do these plots, and for this one, and you've got to fill out the other table. Oops. For the other one, you've got to fill out this one, and that's the assignment. Okay.